Thank you, everybody. Hello. Today I'm going to present on our ongoing project that brings snapshot-based, coverage-guided fuzzing to macOS kernel. This project doesn't have a working code name. It's a common thing for macOS projects to have an Apple-themed pun in their name, but all of them are used up, so I'm open for suggestions. I'm going to breeze through my motivation here a little bit. I'm part of a vulnerability research team in Cisco Talos. One of our major tasks is to perform third-party vulnerability research, which usually culminates in us finding vulnerabilities, reporting them to their respective vendors, getting them fixed, detections for those vulnerabilities being put into our product, and finally, a public disclosure of those vulnerabilities on our website that you can find here on talosintelligence.com. We do report a sizable amount of vulnerabilities each year to Apple. This is a recent list. And macOS is one of our focus targets, I guess. So finding vulnerabilities is our goal, but finding better ways of finding good vulnerabilities is what we work on and trying to improve. Some software is harder to test and analyze than other and requires better tooling as well. I'll walk you through our project that enables us to effectively test fuzz macOS kernel components on commodity hardware with coverage analysis. And we'll get back into what I mean by that. There are sizable difficulties when it comes to fuzz testing on macOS. Compared to fuzzing everything on Linux, where most of the things are open source, fuzzing anything on macOS does have its own difficulties. Things are closed sourced. Most of the things are closed source, so we can't do compile time instrumentation like you can do with open source stuff. You do have dynamic binary instrumentation tools like Frida or Dynamorio and the likes, but you generally can't apply those on kernel components. And last but not least, there are hardware requirements. With very few exceptions, macOS software or macOS runs only on Apple hardware. Yes, you can virtualize it in various ways, but that reduces the attack surface and has its own drawbacks as well. You still need to run that on Apple hardware, and fuzzing on laptop isn't exactly effective. This project aims to alleviate some of those problems. Using snapshot-based fuzzing, we can precisely target the components of the OS that we want to test. We can target the closed-sourced code with actual coverage. We can get full instrumentation. We can run it in an emulator as well, which enables us to scale this up, to run it on our commodity hardware, on our regular Intel servers that we have plenty of and utilized for fuzzing, that we can utilize for fuzzing. So what is snapshot fuzzing? Snapshot-based fuzzing as opposed to regular fuzzing. The simplest way to fuzz stuff is to just run an application in a loop, modify the inputs, and observe it and wait for it to crash. The problem with that is you spend most of the time executing boilerplate code like application startup, initializations, or whatever, instead of actually executing the code that you care about. With snapshot fuzzing, this approach allows you to define a precise point in the code, in the process execution that you want to actually isolate from the rest of the application. You execute only that part of the code. When you get to the end of it, you revert back to the start and start again. So it's more efficient in that way. In terms of snapshot fuzzing, a snapshot of the process includes complete virtual memory of that process and any other resources that it might need, such as CPU state or any other things that you might need to actually restore the process back to the point where you want to start your fuzzing. You just inject your fuzzing test case in memory. Snapshot fuzzing is sometimes also called in-memory fuzzing, and resume execution until you reach a sync point, at which point you stop it, revert everything back to the start point, rinse and repeat, and you wait for things to crash. The benefit of this is that you only pay a penalty for restoring the process. You're not building it from scratch, and you get the benefit of all the OS mechanisms that are there for performance, like copy and write, dirty pages, on-demand paging and so on. We had a previous attempt at snapshot-based fuzzing through our Barbarizer project, which was championed by Corey Duplantis, which was a bare metal hypervisor. Was custom built in Rust from ground up to be a fuzzing-specific hypervisor. It involved acquiring a snapshot of a running virtual machine and then transplanting that snapshot into a bare metal hypervisor for efficient fuzzing. While this showed great potential and gave us a glimpse of the utility of the approach, it had its own drawbacks, so we needed a different solution. And around the time we published Barbarizer, Axel Souchet published his What a Fuzz project, which does the same thing, snapshot fuzzing, but takes a very different approach. It trades performance focus to have a nice development environment by relying on existing tooling. It uses Hyper-V to actually get the snapshots, and then uses KD to dump the state of the virtual machine, saves the CPU state and the memory dump in the Windows file format, Windows dump file format, which is actually optimized for loading already. It's written in C++, which means you can benefit from all the existing tooling and all the code for mutators and so on. On the other side, it has multiple possible execution backends. We'll be utilizing Box, an x86 emulator, which provides complete instrumentation framework. You pay for that instrumentation capability and performance. It's nowhere close to native execution speed, but it does allow for very, very fine-grained control over the execution and instrumentation. And it runs on whatever you can. It's a software emulator. It doesn't rely on virtualization for what it does, so you can run it on Linux, Windows, any other platform, on any other hardware. The biggest downside of What a Fuzz is that it actually targets only Windows virtual machines and Windows and application running on Windows, and we kind of want to fuzz macOS in this case, so we need to do some work. Here's what we need to achieve snapshot-based fuzzing using What a Fuzz framework on macOS kernel. We need to augment it in a way to be able to use it. If we split things in a pre-fuzzing and fuzzing stage, in the pre-fuzzing stage, acquiring the snapshot, we need a couple of capabilities. First is a mechanism to debug the OS and the process that we want to fuzz. This is necessary to precisely control and choose the point of the snapshot, usually through some sort of a breakpoint or something. Then we need once we pause the execution of the whole operating system, we need a mechanism to acquire a copy of physical memory in order to be able to transplant that process to another machine. We need the exact copy of the memory that that's running it. We also need to record the exact CPU state in order to be able to precisely restore the execution environment of that process. This includes not only general purpose registers, but also all the MSRs, the control registers, all the other kind of hidden registers of the CPU. In the fuzzing stage, on the other hand, we need a mechanism to restore the acquired memory pages, so to rebuild that process on a different environment. And we need to build a custom thing for this, for What a Fuzz. We also need a way to catch crashes, as crash handling and exception handling faulting mechanisms on macOS are very different than on Windows, obviously. We also need a way to modify the CPU state and memory itself to be able to inject our test cases and actually perform fuzzing. And we'll walk through how we achieve these steps for this particular project. So in terms of debugging and snapshot acquisition, ideally, we'd want to be able to take a snapshot of an actual physical machine. That would give us the most attack surface with all the kernel extensions loaded, with all the features of the operating system that's running on a laptop already in memory and ready to be used. As there's a significant attack surface reduction when you're looking at the virtualized macOS in something like VMware Fusion. However, debugging physical Mac machines is somewhat difficult. Even on Intel Macs, the old Macs, this isn't straightforward. By the way, all I'm talking here is strictly targeting Intel Macs, not the Apple Silicon. So debugging physical machines is somewhat difficult because it requires an extra machine, it requires special network adapters, and the debug mechanism itself isn't perfect for what we're trying to do. It relies on non-maskable interrupts and other things, and it doesn't actually stop the whole OS from executing. There's still something running in it when you're actually doing physical machine debugging. Debugging a virtual machine, on the other hand, is somewhat easier. VMware Fusion contains a GDB stub that you can enable and connect to that allows you to single step through the OS execution, basically, and you can do whatever you want on it. Also, we can piggyback on VMware's snapshotting feature for snapshot acquiring. So we went with the second option in this iteration of the project, and we rely on VMware's mechanisms to achieve the things we need. So the debugger stub itself is relatively simple to use. You just enable it in your VMX file, the configuration file for the VM. Whenever you start the virtual machine, a port will be open with the listener on it, and on the right-hand side, you can see LLDB connecting to that port. It's just like using any other GDB stub. When you connect to it, if you have KDK installed and all the accompanying scripts, you can use them just as you would over Apple's own debug protocol. With some hoops, might require jumping through some hoops here and there, but for the most part, it works. So this gives us a way to pause and break the execution of the virtual machine at any point we want. We can just place a breakpoint. On the snapshotting side, the second requirement, acquiring the snapshot, we can achieve through Fusion's support for snapshotting as well. The usual way you use VMware Fusion snapshotting is to either suspend the VM or save the state of it, but we're gonna subvert it slightly to do what we want. The way we use it here is we set a breakpoint in the debugger at the point where we want to stop the execution. We wait for that breakpoint to be caught, to execute, and then take a snapshot. When the breakpoint is executed and you drop back to a debugger, you can still take a snapshot of that running process and you get the machine at the stop state. A slightly more difficult part of this is figuring out how to use those snapshots. It turns out that VMware snapshot files or snapshots themselves are composed of two files. One is a vmem file, and the other one is a vmsn file. A vmem is just a dump of the physical memory of the virtual machine. It's a linear dump. Like if a virtual machine has 2 gigs of RAM, the vmem file will be byte-for-byte copy of those 2 gigs of RAM. It gets slightly more complicated if you have more, but for the most part, it's just a linear dump. It's easy to reuse. The machine state file, on the other hand, is somewhat more complex. It's undocumented file format and contains a lot of stuff that's necessary for resuming a virtual machine, but that we don't care about, so we can kind of skip it. But we need to dig into it to extract the data that we actually need. It's largely undocumented, but has been mostly reverse engineered for use in volatility projects. In my particular version of target macOS and VMware Fusion, the support for it in volatility was slightly broken, but it was easy to fix and patch it to dump out only the necessary information that I want. And here in the right-hand side, you can see a chunk of CPU state that I dump out from the snapshot file. You can see CPU internal registers like IDTR, LDTR, and others that are relevant for execution. There's obviously, CPU state is larger, but wouldn't fit in a screenshot. Wouldn't fit in a slide. If we go back to the fuzzing side of things, with both file formats figured out, we have our snapshot. We need to figure out how to actually restore that snapshot. We need to modify WhatAFuzz to be able to load that raw memory dump into appropriate structures. As WhatAFuzz was built to use Windows memory dumps with its file format, we need to kind of fake those a little bit, which is super easy, just requires a couple of lines of C code to emplace that physical memory in the right structures to support on-demand paging and so on. So that part is relatively easy. And with those out of the way, we're kind of good to go. After some inevitable debugging to correct some mistakes about CPU state, turns out LLDB will happily lie to you about the state of some of the registers, or VMware rather would lie to you about it. After some debugging, you actually get to a point where you can execute some code. This here shows an example of a snapshot created on macOS, taken with VMware Fusion, moved onto a Windows machine, loaded into our modified version of WhatAFuzz, and then resumed. And here, if we ignore a bunch of debug output, we can see that this trial run has executed a total of about 13,000 instructions, has touched a bunch of memory, and has done so relatively quickly. This tells us that the code did actually run. It ran a certain amount of code, and this was kind of the proof of concept that I was looking for. It's a simple example, but what's left for actual fuzzing is just minor details at this point. What's important here is that we know how much code we've executed, which tells us that we do actually have coverage information, which is necessary for any actually viable fuzzing. One other thing that we need to solve that every fuzzer kind of needs is a way to catch crashes, to distinguish benign test case executions from the ones that cause something untoward. The way WhatAFuzz does that and the way we need to do it here is as easy as setting up a breakpoint. We just need to find a good place for that breakpoint. So what's that appropriate place? On macOS, kernel panics, exceptions, all sorts of faults go through a relatively complex call stack of functions that get executed when an exception or a fault happens, which ultimately culminate with one of these screenshots that you've probably seen before if you mess something up on your macOS. And it turns out one of the functions in that call stack is a good choice to set a breakpoint on, called exception triage, because when that function is called, its parameters contain all the necessary information about the crash, about the exception itself, so that we can use to kind of illustrate our crash and distinguish it from a different one. So in order to catch crashes, we just set a breakpoint on exception triage function, and when that gets hit, we know something bad has happened to that macOS kernel. So let's see how the fuzzing, a concrete example, would work. Let's say we wanted to target something relatively simple, tangible. In this case, I'll showcase targeting IPv6 networking stack. It's a simple entry point, but it's an entry point to a very complex code base. And it's open source, so it's kind of a nice illustrative example. This is an interesting attack surface because it's comprised of a fairly complex set of protocols. It's reachable over network, and any crashes in this would be kind of interesting. I don't have my hopes up for this turning up any crashes because this code has been tested before, but again, it's a nice illustrative example. Additionally, it would be relatively difficult to fuzz with the traditional fuzzers because network fuzzing is slow, you wouldn't have coverage, and so on, because this runs in the kernel. To cut the long story short, our fuzzing target, our snapshot point, is the entry of the IP6 input function, which is the entry point where IPv6 packet parsing happens. And it has a single parameter. The function has a single parameter, which is an mbuff that points to the packet data. mbuffs are a fairly standard structure in GNU, and it's essentially a linked list of buffers that contain the data. In this case, packet data. When we want to fuzz this, we just need to find where the actual packet data is and mutate it before resuming execution and continuing the testing. So first step after defining our target is actually acquiring the snapshot. And to create a snapshot, we first use a debugger to set a breakpoint at IP6 input function using just LLDB that's connected to our debug stub. This is just like using LLDB in any other way. You just set a breakpoint on whatever you want. Then you need a way to provoke that breakpoint. You need to catch it somehow to get it to execute. You can either wait for the VM to receive an IPv6 packet, at which point the breakpoint will be hit, or you can just send an IPv6 packet yourself with controlled data and set it up nicely for fuzzing. Here I've used ping to send an IPv6 packet to the target VM. And as soon as I send ping, execute ping, the breakpoint is hit and the kernel execution is stopped, so we can take our snapshot. After taking a snapshot through VMware, that's kind of simple. We've already seen that. We need to set up our fuzzing harness on the other hand. We need to tell two things to the fuzzer itself. When does the test case stop? In this case, we consider it done. We consider the packet processing done when IP6 function returns. So we put a stop at the end of it. And we also need to tell it what constitutes a crash. And that's all basically that we need from the harness, from the fuzzing setup side of things. From the actual fuzzing side in the harness, we need to locate that M buffer, mutate the data in it, make sure that the structure is sane, and that's done with just a couple of lines of C where we actually take the mutated test case, put it in memory, and set up some other size values. So that's relatively simple. And with that, we can actually start fuzzing the IP6 input function. This is how it looks like when you start it. There's a couple of things we can see here. Lines that start with saving output means that our fuzzer is uncovering new code. It's hitting new code. The coverage is increasing, which is good. And we can see something about a little bit of stats too. We're getting about 1,000 executions per second with just a single node, with just a single core that's actually fuzzing in this case. And our coverage that we're getting is constantly increasing. We don't see any crashes, but I wasn't holding my breath for crashes when targeting this code anyway. And just to reiterate what we've done here, we have captured a snapshot of a running virtual machine that was running on a Apple laptop. We transplanted it onto whatever platform, on Windows in this case for testing. We started fuzzing it there, executing it under an emulator, and at this point we can scale it up. We can distribute it across many cores that we have, many cheap server cores that we have under on our fuzz farm or whatever. And with that, we can kind of achieve higher speeds. No fuzzer would be complete without some additional support tooling, because you need to introspect your fuzzers as well. You can't just blindly fuzz stuff. One of those is we've implemented all of these because they're necessary for actually analyzing what's going on. That includes test case tracing. You need to be able to tell what code the test case is actually executing. It's also helpful for debugging both the fuzzer and the fuzz target if you can symbolize those test cases, because you want to be able to see what code has been executed with function names. Otherwise, just looking at the addresses doesn't bring you much. And kind of building on that, we have some coverage analysis tools that import these results into IDA Lighthouse, which lets you visualize it. This is how it looks like. The symbolized test case trace on the left, and a colored IDA graph on the right, which lets you see what your fuzzer is actually doing. And think with that, there's some further work to be done that I'm looking forward to. There's some further work to be done that I'm not looking forward to, but I do want to target more of the macOS kernel code. We've targeted some of the components, but definitely haven't exhausted all of them. One interesting thing to do would be to use syscaller style structure-aware fuzzing. That would require some additional code. And like kind of wishful thinking side of things, getting something similar running on Apple Silicon would be super interesting. And with that, I would like to hear if you have any questions, but I think I'm out of time. So I'll be around the conference, and please just come and bug me. Thank you very much.
Thanks again. Super interesting stuff, for sure. So yeah, unfortunately, we